Advanced technology thrived long before our modern world took shape. By the end of this journey, you will see human history as a story of incredible peaks and puzzling declines. We will uncover 25 ancient machines, from a 2,000-year-old astronomical computer to precision stonework that defies explanation. How could such sophisticated knowledge simply vanish from the world? And what does a forgotten age of scientific mastery reveal about our own potential? What does it mean for a civilization's greatest achievements to be lost to time? Divers exploring a shipwreck off the coast of a tiny Greek island in the early 20th century pulled a lump of corroded bronze and wood from the seafloor. It looked like a formless rock crusted over by 2 millennia underwater. No one could have guessed this unassuming find would become one of the most significant archaeological discoveries of all time, a device that would shatter our understanding of ancient technology. This was the Antikythera Mechanism. Years of painstaking research using advanced X-ray and imaging technology revealed the truth. It was not a rock, but an incredibly sophisticated astronomical calculator, a complex clockwork of at least 30 interlocking bronze gears housed in a wooden case. Think of it as the world's first known analog computer, a device of breathtaking genius crafted in the 2nd century before the Common Era. Its intricate gears moved to simulate the motions of the sun, the moon, and the 5 planets known to the ancient Greeks. It could predict lunar and solar eclipses with remarkable accuracy, and it even tracked the 4-year cycle of the Olympic Games. The level of miniaturization and mechanical complexity seen in its gear trains would not be seen again in Europe until the development of mechanical clocks in the 14th century, over 1,500 years later. How did a civilization without industrial tools achieve such precision? The inscriptions on its casing, now being read with high-resolution surface imaging, serve as a detailed user's manual for the cosmos, revealing a deep understanding of cycles and mathematics. This was not a toy, it was a tool for serious scientific inquiry. The existence of the Antikythera Mechanism forces us to ask a profound question. If such a masterpiece of engineering was on a ship, likely being transported, it implies a center of learning where this knowledge was developed and taught. Who were the masterminds behind its creation, and what happened to the school of thought that produced it? The fact that this technology seemingly vanished, only to be reinvented more than a millennium later, suggests that scientific mastery can be a fragile flame, easily extinguished by the winds of time. This single device, salvaged from the deep, opens a window onto a forgotten age of innovation, making us wonder what other marvels still lie hidden, waiting to be found. While the Antikythera Mechanism redefined our view of ancient Greek mechanics, a far simpler set of artifacts from Mesopotamia presents a different kind of puzzle. In the 1930s, workers excavating for a railway near Baghdad uncovered a collection of peculiar clay jars. Each jar contained a copper cylinder, and within that cylinder sat an iron rod, all sealed with an asphalt plug. To the untrained eye, they appeared to be nothing more than odd storage containers, perhaps for sacred scrolls. But when archaeologists assembled these components and added an acidic liquid like vinegar or grape juice, they made a startling discovery. The jar became a basic battery capable of generating a small but measurable electric current. This was the Baghdad Battery, a device potentially 2,000 years old. Theories about its purpose are as fascinating as the object itself. Some researchers suggest it could have been used for electroplating, applying a thin layer of gold or silver onto other metal objects. This would explain the presence of gilded artifacts from the same period that seem to lack evidence of traditional fire gilding techniques. Others propose a medical application where the mild electric shock was used for therapeutic or ceremonial purposes, a practice known in other ancient cultures. Yet, without written records explicitly describing its use, its true function remains one of history's great debates. Quotes from archaeologists highlight this division, with some calling it a clear power source and others cautioning that it might have been a storage vessel for something entirely different, with the electrochemical reaction being a mere coincidence. Modern recreations have proven its viability beyond doubt, using replicas built exactly to the original specifications and filled with an acidic electrolyte. Experimenters have consistently produced a voltage of around 1 to 2 volts. It is not enough to power a light bulb, but connecting several batteries together in a series could have created a significant charge. Imagine the awe of an ancient artisan who, perhaps by accident, first felt the mysterious tingle of this invisible force. The very existence of such a device, however, forces a larger question. If this was a known technology, why did it not lead to a wider electrical revolution? Its limited geographical find and the lack of any clear evolution in the design suggest it was a localized innovation, a spark of genius that either was not understood or was not valued enough to be passed down and developed further. This glimpse into a potential ancient understanding of electricity reveals a scientific tradition that was perhaps fragmented, where brilliant ideas could appear and then vanish without a trace. From the subtle spark of a forgotten battery, we arrive at the colossal, thundering power of water harnessed on an imperial scale. The Roman aqueducts were not merely channels for water, they were the very arteries of the empire, machines of stone and gravity that sustained cities of millions. Picture clear mountain water flowing for dozens of miles, not by pumps or motors, but by the unwavering pull of gravity alone. Roman engineers mastered this principle with breathtaking precision, designing channels with a steady, gentle slope that dropped only a few feet for every mile of distance. This required an intimate understanding of the land, achieved with simple yet effective tools like the chorobates, a sophisticated leveling instrument that ensured water would always find its way downhill. The sheer ambition is staggering. Structures like the Pont du Gard in France, a massive 3-tiered aqueduct bridge, stand as monuments to this ambition, carrying water high across a river valley. But the true genius of Roman water management lay not just in delivery, but in application. At places like the Barbegal Mill complex in southern France, water was transformed into raw industrial power. Here, a single aqueduct fed a cascading series of 16 separate water wheels, creating a massive factory capable of producing enough flour every day to feed the entire population of the nearby city of Arelate, estimated at over 10,000 people. This was not a small-scale operation. It was industrial-scale milling powered entirely by renewable energy, a concept that would not become common again for over 1,000 years. Modern civil engineers still express awe at the durability of these structures, a resilience born from revolutionary Roman concrete and the brilliant use of the arch, which distributed weight perfectly to create those iconic, enduring forms. These were machines built to last centuries, and many of them did. So what happened to this mastery, the knowledge of how to build and, just as importantly, how to maintain these vast networks did not disappear overnight. It faded gradually as the complex social and economic systems that supported such public works fractured. The aqueducts themselves did not fail, the society that built them did. This invites a sobering reflection on the fragility of even the most advanced infrastructure and how easily the gears of industry can grind to a halt when collective knowledge is lost. The legacy of Roman water engineering leads us to wonder what other forms of power, just as fundamental, were mastered and then forgotten by even older civilizations. Centuries before the Industrial Revolution, a brilliant mind in Alexandria harnessed the power of steam. The inventor Heron described a device he called an eolipile, a seemingly simple contraption that was centuries ahead of its time. Imagine a hollow metal sphere mounted between two pipes which acted as bearings, allowing it to spin freely. These pipes fed steam from a heated water boiler into the sphere. Two more bent tubes or nozzles protruded from opposite sides of the sphere. As the steam rushed out through these nozzles, the reactive force, much like a releasing balloon, caused the entire sphere to whirl with surprising speed and power. This was not just a curiosity, it was the world's first documented steam turbine, a clear demonstration of converting thermal energy into mechanical rotation, a fundamental principle of jet propulsion. Historians of technology often point to the eolipile as a theoretical masterpiece, a proof of concept that showed a deep understanding of physics, yet it remained, for the most part, a temple wonder. Heron and his contemporaries in the vibrant intellectual hub of Hellenistic Alexandria created many such marvels. His published works detailed automatic temple doors, a coin-operated holy water dispenser, and a wind-powered organ, all showcasing a culture rich in engineering ingenuity. So why did this revolutionary steam engine not power factories or propel ships? The answer seems to lie not in a lack of intelligence, but in a lack of necessity. The ancient economy was built on abundant human and animal labor, with slavery providing a cheap and readily available workforce. There was simply no driving economic pressure to replace muscle with machine on an industrial scale. The eolipile was a solution in search of a problem, a spark of genius that never found the right tinder to start a fire. It stands as a poignant reminder that scientific discovery alone is not enough. It requires a society ready to embrace its potential. This brilliant but unapplied engine makes us wonder how many other world-changing inventions were conceived as mere novelties, their true power lying dormant for ages. From the earthly power of steam, our gaze now turns upward to machines that sought to map the heavens themselves. The granite boxes inside the Serapeum of Saqqara present a mystery that defies simple explanation. Carved from immensely hard stone like rose granite and basalt, their surfaces are flawlessly smooth, with corners so perfectly sharp they seem machined. The real enigma, however, lies within. Deep, cylindrical holes were bored into this incredibly resilient material, and the evidence left behind in these drill cores tells a story that challenges our entire understanding of ancient tools. When archaeologists examined these granite cores, they found spiral grooves cut into the stone with a uniformity and depth that suggests a drill bit capable of immense, sustained pressure and a remarkably fast, consistent rotation. This is not the kind of mark a handheld copper tool, even with sand as an abrasive, can easily produce. The feed rate, the amount of material removed with each rotation, appears to have been greater than what seems possible with primitive technology. Geologists who have analyzed these cores note that the grooves are too regular, too deep, and too smoothly cut. It is as if the drill did not merely scrape and grind, but practically flowed through the stone like a hot knife through butter. How could such a feat be achieved? The most common theory points to the use of a bow-driven drill, where a long staff with a hard stone bit is spun back and forth by a bowstring. Yet, to achieve the results seen in the granite, this simple tool would have needed to be scaled up into a massive machine, capable of applying tons of downward force and maintaining a rapid, uninterrupted rotation. Some researchers propose a system of weighted beams and pulleys to provide the necessary pressure, turning a simple hand tool into a powerful piece of industrial equipment. The ancient artisans likely used a clever abrasive slurry, perhaps a mix of quartz, sand, and water, which is harder than granite, to do the actual cutting. But the precision of the boreholes, some several feet deep, suggests the drill itself was remarkably stable and vibration-free. Imagine the sound of such a workshop, the rhythmic hum of a massive drill spinning, the smell of crushed stone, and the sight of craftsmen guiding a machine that bit steadily into rock thought too hard to work. What skills and knowledge were required to operate such a device, and why did the specific techniques for this level of precision not survive in the historical record? This mastery over stone, so evident in the silent perfection of an Egyptian sarcophagus, forces us to reconsider the workshop not as a place of simple chisels, but as a potential hub of advanced mechanical innovation. Such profound control over the very earth beneath their feet logically leads us to wonder how these ancient cultures moved the colossal fruits of their labor. The Syracusia was a marvel so immense it blurred the line between ship and floating city. Commissioned by King Hiero II of Syracuse and designed by the legendary mind of Archimedes around 240 BC, this vessel was the ultimate expression of Hellenistic naval ambition. Ancient sources describe a colossus requiring so much timber that its construction nearly denuded entire forests of Sicily. Its sheer scale is difficult to grasp, estimated to have been longer than a modern football field, capable of carrying almost 2,000 tons of cargo alongside hundreds of passengers and a contingent of soldiers. But its true genius was not just in its size, but in the mechanical innovations that made it functional. Archimedes designed a revolutionary water pump system, a massive screw housed within a wooden casing, which allowed a small crew to efficiently bail out the bilge water that would otherwise sink such a heavy ship. This was engineering on a monumental scale. The ship was a palace afloat, adorned with mosaic floors, a library filled with books, a gymnasium for exercise, and even a dedicated temple to the goddess Aphrodite. Its promenades were lined with lush gardens and shaded by ivy-covered walkways. To load its vast holds, it employed a system of cranes and hoists, another innovation likely guided by Archimedes' principles of leverage and mechanics. Some accounts even suggest it was equipped with a powerful catapult-like weapon, a forerunner of artillery, designed to hurl massive stones for defense. This was not merely a trading vessel, it was a tool of diplomacy and a floating statement of power, sent on a grand voyage to deliver its extravagant cargo to Ptolemaic Egypt. Consider the immense organization required for such a project, the funding, the coordination of countless artisans, the management of scarce resources like timber and pitch. How did a single city-state muster the economic and administrative power to build and maintain such a leviathan? The Syracusia represents a peak of naval engineering that would not be rivaled for centuries. Yet, after its celebrated maiden journey, the great ship vanishes from the historical record, its fate as mysterious as the depths it once sailed. This nautical wonder, a machine of wood and wind, demonstrates that ancient mastery extended far beyond static structures, conquering the very seas with organized, systematic brilliance. Far from the open seas, another ancient machine offered protection from a far more unpredictable danger. In the year 132 of the Common Era, a Chinese scholar and inventor named Zhang Heng presented the Han court with a remarkable creation, a bronze urn adorned with 8 dragons, each holding a bronze ball in its jaws. Below them, 8 corresponding toads sat with their mouths open, waiting. This was the world's first seismoscope, a device designed to detect the direction of an earthquake from hundreds of miles away. The concept was revolutionary, a machine that could sense a tremor too distant for human perception and point toward its origin. Historical accounts describe its stunning accuracy. On one occasion, the device triggered a ball to drop without any local shaking. Skeptical officials dismissed it as a malfunction until days later, when a messenger arrived from a region far to the west, reporting a major earthquake. The dragon facing that direction had given the warning. How could such a device possibly work without any modern electronics? While the original internal mechanism has been lost to time, historians of science propose a beautifully simple principle based on inertia. Inside the ornate urn, they believe a heavy pendulum was suspended. When seismic waves, the vibrations traveling through the earth, arrived from a specific direction, they would cause the pendulum to swing. This motion would then trigger a clever series of levers or tilting arms, pushing one of the dragons to release its ball into the waiting toad below. The design was a masterpiece of indirect measurement, transforming an invisible force into a clear, visual signal. Modern engineers have built replicas based on these theories, and many have successfully detected test vibrations, proving the concept was not just legend but viable technology. This was more than a scientific instrument. It was an early warning system for an empire, a tool that could alert the government to send aid to a stricken region long before word could travel by horseback. It reflects a profound understanding that the Earth itself communicates through motion, and that by listening carefully we can anticipate hardship. The very existence of Zhang Heng's Seismoscope makes you wonder what other natural rhythms, from weather patterns to magnetic fields, were being measured by forgotten devices. This pursuit of predicting the unpredictable leads us directly to another fundamental human challenge: the precise measurement of time itself. High up in the Andes, the stone walls of the Inca stand as a silent testament to a lost engineering art. Blocks of granite, some weighing over 100 tons, are locked together so perfectly that you cannot slip a piece of paper between them. This is not simple stacking. It is a colossal, three-dimensional stone puzzle assembled with a precision that seems to defy the tools of the era. How did a civilization without iron tools or the wheel achieve such a seamless, monolithic fit? The mystery deepens when you look closer. The surfaces of these stones are not flat in a conventional sense. Instead, they feature subtle, rounded bulges and corresponding hollows, creating complex, interlocking joints that are far stronger than any simple flat plane. Modern stonemasons who study these walls express a mixture of professional admiration and complete bafflement. The prevailing theory suggests the Inca used a process of persistent trial and error, repeatedly placing a stone, marking the high points on the opposing face, and then patiently pecking away at those spots with harder stones like hematite. They likely used sand and water as a fine abrasive to smooth the final fit. Yet, this explanation alone struggles to account for the sheer scale and the geometric complexity seen at sites like Sacsayhuaman, where zigzagging walls feature stones with as many as 12 distinct angles, each meeting its neighbor with microscopic accuracy. Some researchers propose more experimental ideas, such as the use of plant acids to soften the stone surface slightly, making it easier to work, or even the guided application of heat and cold to induce controlled fractures along natural crystalline lines. These theories point toward a profound, intuitive understanding of materials science, a knowledge gained through generations of working intimately with the mountain itself. The logistical challenge only adds to the awe. At a place like Ollantaytambo, these massive blocks were quarried from a mountainside across a deep river valley, transported up steep slopes, and then lifted into place. The organization required for such a feat is staggering, implying a society with advanced project management skills and a deep mathematical understanding of geometry and stress distribution. This stone mastery, designed to flex and settle without collapsing during the region's frequent earthquakes, has kept these walls standing for centuries while modern buildings around them have fallen. What does this say about a culture that could read the land so perfectly and shape it with such enduring strength? The seamless fit of these stones, achieved without any mechanical fasteners, hints at a technological philosophy where the machine was not a separate device, but the very process of construction itself, a symphony of patience, observation, and an almost supernatural control over solid rock. Such a profound connection to the Earth's materials makes the next step in our journey almost inevitable: to explore the machines that moved these mountains. The sheer mass of an Inca stone block presents a monumental challenge, but moving water requires a different kind of genius, one that works with fluidity and flow. For civilizations built along great rivers, lifting water from a low source to high fields was the difference between harvest and hardship. The solution was both elegant and enduring: the Archimedes Screw. Its design is deceptively simple: a helical surface wound around a central cylinder, enclosed within a watertight tube. When one end is lowered into a water source and the entire assembly is tilted and rotated, magic happens. The turning motion traps pockets of water within the spiral chambers, carrying them steadily upward along the tube until they pour out from the top. It is a continuous, gravity-defying flow powered by nothing more than a hand crank or the push of a river current. While its invention is attributed to the brilliant Archimedes in the 3rd century before the Common Era, evidence suggests similar devices were used even earlier in ancient Egypt for irrigation, hinting at a widespread understanding of this fundamental principle. Mechanical engineers today still point to the screw as a masterpiece of fluid dynamics. They explain that it operates on an inclined plane, one of the basic simple machines, but wrapped into a spiral. This design minimizes turbulence and energy loss, making it incredibly efficient at moving not just water, but also granular materials like grain or sand. Its adoption was rapid and far-reaching. Roman miners used massive, human-powered screws to drain water from deep pits, a crucial application that enabled them to reach previously inaccessible ore. Farmers across the Hellenistic world and later in medieval Europe relied on it to water their terraced fields. The design was so perfectly suited to its task that it never became obsolete. Modern versions, often powered by electric motors, are used worldwide for moving wastewater, controlling irrigation in agricultural fields, and even in some types of industrial machinery. Why would such a brilliantly effective and simple machine ever fade from use in some regions? The knowledge of how to build it was sometimes lost in periods of social disruption, when the specialized craftsmen who understood its construction were no longer there to pass on their skills. In other cases, larger, more centralized systems like Roman aqueducts may have made local screws seem less critical, until those grand systems themselves fell into disrepair. The screw's survival is a testament to the power of a design that is both intelligent and accessible, a tool that turns the basic force of rotation into a lifeline for civilizations. This elegant solution for raising water from the depths makes us wonder about the machines designed to plunge into them, to explore the world beneath the waves. The silent, patient strength of Inca walls stands in stark contrast to the dynamic mechanical muscle that reshaped the Greek landscape. To raise the columns of the Parthenon and lift the massive blocks for temples and monuments, Greek engineers developed a revolutionary technology: the crane. Simple hoists had existed for centuries, but the Greeks perfected them into powerful machines that fundamentally changed architecture. The key innovation was the compound pulley, a system of multiple wheels that dramatically multiplied human strength. By threading a rope through several grooved sheaves mounted in a block, a single worker could lift weights that would otherwise require a team of 50. This was mechanical advantage in its purest form, a clever redistribution of force that turned one person's pull into a titan's lift. Historical accounts credit brilliant minds like Archimedes with refining these systems, with stories suggesting he single-handedly pulled a fully loaded ship ashore using a complex arrangement of pulleys. These cranes were not simple tools, they were sophisticated machines. They incorporated a winch, a rotating drum around which the rope was wound, providing controlled, incremental lifting power. A ratchet and pawl mechanism acted as a safety lock, preventing the heavy load from slipping back down. Different types of cranes emerged for specific tasks, from the three-legged tripod used for stable, vertical lifts to the more versatile derrick crane with its long, rotating boom that could swing blocks into precise position. Imagine the scene at a site like the Parthenon, the air filled with the creak of ropes and the rhythmic clicking of winches. Teams of workers would turn the massive drums, their coordinated effort guided by a foreman's shouts, as a multi-ton marble block rose steadily into the sky, hovering for a moment before being gently guided onto its waiting course. This was not brute force, it was controlled, calculated power. The precision these machines allowed is evident in the flawless fit of the stones themselves, a level of accuracy that would have been nearly impossible with just ramps and levers. How was this intricate knowledge of physics and mechanics passed down? It likely moved from master to apprentice in busy workshops, a fragile chain of understanding that could be broken by social upheaval or the loss of a single great mind. The crane did not just build temples, it built the very idea of a skyline, enabling civilizations to reach literally and metaphorically for the heavens. This mastery over weight and height, over making the impossibly heavy seem light, naturally leads our curiosity toward the machines that conquered distance, the automotive wonders that moved entire societies. The gleam of ancient gold is more than just wealth, it is a testament to a forgotten science of metal. Across the highlands of South America, cultures like the Muisca and the Chavin developed chemical processes so advanced they could transform raw ore into objects of breathtaking artistry and spiritual power. Their secret was a mastery of heat and chemistry, a technological leap that went far beyond simple hammering. The lost wax casting technique they perfected is a marvel of engineering. An artisan would first sculpt a detailed figure from beeswax, then encase it in a thick layer of clay, leaving a small channel. When this clay mold was fired in a kiln, the wax would melt and drain out, leaving behind a perfect hollow cavity. Molten gold, heated to temperatures exceeding 1,000 degrees Celsius, was then poured into this void. Once the metal cooled and solidified, the clay shell was broken away to reveal a flawless golden object, its intricate details preserved forever. This method allowed for the creation of stunningly complex works, like the legendary Golden Raft, a detailed scene depicting a chieftain and his court that forms the very heart of the El Dorado legend. But the innovation did not stop there. Some metallurgists studying these artifacts suggest these cultures may have even understood the principles of mercury amalgamation, a process where liquid mercury is used to bind with fine gold particles, separating them from worthless ore. This paste could then be carefully heated, vaporizing the toxic mercury and leaving behind pure, concentrated gold. The sheer knowledge required to safely handle such materials and control these volatile reactions speaks to a deep, experimental understanding of chemistry. Museums today display these golden offerings, from delicate nose rings to ceremonial masks, each one a silent witness to a sophisticated industrial process. Why would a society pour such immense resources and intellectual energy into this craft? The answer lies in a world where metal was not merely currency, but a sacred substance, a conduit to the gods and a symbol of cosmic order. This chemical mastery, so evident in the enduring beauty of a golden artifact, makes us wonder what other elements of the natural world they sought to measure and control. Our journey now turns from the chemistry of the earth to the machines that mapped the heavens. A treasure hunter's metal detector did not find coins or jewelry in a German forest, but instead a corroded bronze disc that would rewrite our understanding of the Bronze Age mind. The Nebra Sky Disc, discovered alongside swords and other artifacts, is a stunning work of art and a potential scientific instrument. Made around 1,600 years before the Common Era, its surface is inlaid with gold symbols representing a crescent moon, a full sun or perhaps a full moon, and a cluster of stars identified as the Pleiades. Two golden arcs along the sides and one at the bottom add to the celestial map. Researchers are deeply divided on its primary purpose. Was it a sophisticated agricultural calendar, a portable observatory for tracking the seasons, or a powerful religious object depicting a sacred mythology? The skill of its creation is undeniable. An artisan carefully hammered the gold symbols onto the bronze base, a technique requiring immense patience and precision. The materials themselves tell a story of far-reaching trade, with the copper likely originating in the Alps and the gold possibly sourced from rivers in Cornwall, England. This suggests the disc was not an isolated wonder, but the product of a network connecting distant tribes across Europe. How did the knowledge of solstices and star patterns, necessary to create and use such a device, travel across such vast distances without a written language? If you held this disc, you could potentially align its arcs with the horizon, using it to determine the correct times for planting and harvest by marking the sun's changing path throughout the year. The central cluster of stars, the Pleiades, appears in the spring sky, a signal known to farmers and sailors for millennia. This single object blurs the line between science and spirituality, between an astronomer's tool and a shaman's sacred relic. It proves that the drive to comprehend the heavens is a human universal, emerging independently in cultures separated by continents and oceans. The disc is a silent witness to a shared, ancient longing to find order in the cosmos, a quest that would soon be applied to the most intimate frontier of all, the human body. The human body itself became a frontier for ancient engineering. In the bustling medical schools of the Roman Empire and along the banks of the Ganges in ancient India, healers wielded tools of startling sophistication. These were not crude implements, but precision-crafted surgical instruments made from bronze and iron, their designs so effective they would be recognizable in an operating room today. Archaeologists have uncovered extensive sets of these tools, from slender scalpels with replaceable steel blades to intricate bone drills, delicate forceps for extracting objects, and specialized hooks for retracting tissue during procedures. The level of craftsmanship is breathtaking. Medical historians note that Roman smiths often used a combination of casting for complex parts and fine forging for sharp edges, creating instruments that were both durable and perfectly balanced in the hand. Texts like the Sushruta Samhita from India, composed centuries before the Common Era, provide detailed descriptions of over 120 different surgical instruments and their uses in complex operations. This text describes procedures for reconstructing noses using skin grafts, removing bladder stones, and even performing early forms of cataract surgery. Imagine a skilled practitioner in ancient India using a tool called a Jabamukhi Saloka, a specialized needle-like instrument, to gently displace a clouded lens and restore a person's sight, all without modern anesthesia or sterilization. How did they manage the very real challenges of infection and pain? Research suggests they developed advanced sterilization techniques, boiling tools in hot water or using antiseptic substances like vinegar and turmeric. Plant-based anesthetics derived from substances like opium and wine were employed to ease suffering. This was not mere guesswork. It was a systematic, evidence-based approach to healing built on generations of careful observation. The existence of such refined tools forces a profound question. What does it mean that these cultures possessed the knowledge and the skill to intervene so directly in the human form, only for much of that specialized understanding to fade from common practice in later centuries? These ancient medical machines, extensions of a healer's will, represent a lost chapter in our relationship with well-being. They remind us that the quest to mend the body is as old as civilization itself, a drive that would soon be applied to a different kind of sustenance born from the soil. In the heart of a sun-scorched desert, survival depends on a hidden secret flowing deep beneath the sand. Ancient Persian engineers faced an impossible challenge: how to bring life-giving water to the surface in a land where rivers rarely ran and the sun ruled supreme. Their answer was not a grand aqueduct stretching across the sky, but something far more ingenious, a machine hidden entirely underground known as the Qanat. This was not a single structure, but a sprawling, subterranean network designed to tap into mountain aquifers and guide the water across dozens of miles using nothing but gravity. The engineering was both simple and profound. It began with a mother well dug deep into the water table at the foot of a mountain. From there, a gently sloping tunnel was carved horizontally toward the destination, a city or a field. But how do you dig and maintain a miles-long tunnel deep underground? The solution was a series of vertical access shafts dug from the surface down to the tunnel's level at regular intervals. These shafts provided air, allowed for the removal of excavated material, and served as permanent maintenance portals. The precision required was staggering. Surveyors using basic levels had to ensure the tunnel's slope was perfect, just enough to keep the water flowing steadily without eroding the channel or letting it stagnate. Geographers and historians often describe the Qanat as one of the most sustainable water management systems ever conceived. Because the water traveled underground, it was protected from the blistering sun, drastically reducing evaporation loss compared to open canals. The system was inherently efficient, delivering a constant, reliable flow that transformed barren landscapes into lush, productive oases. An entire city could rise around the mouth of a Qanat, where the tunnel finally met the open air, creating a vibrant hub of gardens, farms, and community life. The construction of a Qanat was a monumental communal effort, a project that could take years and required the coordinated labor of an entire village. This was not a technology imposed by a distant king, but a grassroots innovation born from collective need. The knowledge of how to build them spread along the Silk Road, from Persia across North Africa and even into Spain, wherever people battled aridity. Reflecting on these ancient waterways, one must wonder about the generations of tunnelers who passed down their skills. How did they maintain these dark, narrow passages over centuries, ensuring the lifeblood of their community never stopped flowing? The Qanat stands as a quiet monument to a different kind of mastery, one of patience and profound understanding of the hidden earth. This legacy of harnessing nature's flow with such elegant efficiency paves the way for a very different expression of ancient genius, one that sought not just to sustain life, but to imitate it through mechanical marvels. The same principles that lifted water and carved stone were also used to create life. In the workshops of Alexandria, engineers like Heron constructed machines that seemed to possess a will of their own, powered by hidden forces of air, water, and steam. These were the automata, the self-operating devices of the Hellenistic world. Far from simple toys, they were sophisticated displays of mechanical genius, often built for temples to inspire awe and devotion among worshippers. A temple's massive doors would swing open as if by an unseen hand when a priest lit a fire on a distant altar. The secret was a clever system of pneumatics, where the heat from the fire expanded air in a sealed container, forcing water through a pipe into a suspended bucket. The weight of the filling bucket, acting through ropes and pulleys, would slowly turn the doors on their pivots, creating a miraculous spectacle. Other automata were designed purely for wonder. A miniature theater would present an entire play with moving figures, their actions driven by a complex arrangement of winding strings, falling weights, and rotating drums. Birds would seem to sing on command, their whistles powered by steam forcing air through tiny pipes. Classicists studying Hero's surviving manuscripts describe these devices as the pinnacle of playful engineering, where the laws of physics were harnessed not for labor but for pure, breathtaking illusion. Reconstructions in modern museums prove these designs were not just fantasies, they were fully functional mechanical performances. What does it say about a culture that its greatest minds devoted such energy to crafting marvels? In an age where the line between the divine and the mechanical was beautifully blurred, these creations were more than entertainment. They were a form of philosophical inquiry, an exploration of how motion could be programmed and life could be imitated. This ancient foray into a kind of robotics reveals a society deeply curious about the nature of control and animation. That same drive to orchestrate complex motion with precision would soon be applied on a far grander scale, to the very tools that shaped the ancient world's most enduring monuments. The Pantheon's dome has defied the elements for nearly 2,000 years, a perfect sphere of concrete cast in space. Its survival is no accident, but the result of a revolutionary material science that modern engineers are only now beginning to fully grasp. This was Roman concrete, a recipe that transformed soft volcanic ash into a stone harder than nature's own. Its secret ingredient was pozzolana, a fine, reactive volcanic dust mined from regions like Pozzuoli. When Roman builders mixed this ash with lime, water, and chunks of rock aggregate, they initiated a slow-burning chemical miracle. The mixture created a crystalline structure that actually grew stronger over centuries, a stark contrast to modern Portland cement which can weaken and crack in decades. Materials scientists studying samples from ancient harbors express genuine astonishment at its properties. They note that the long-term chemical reaction produces a mineral that effectively fills any tiny cracks that form, giving the concrete a remarkable self-healing ability. Seawater, the great destroyer of modern concrete, becomes the very catalyst that strengthens the Roman version, making harbor walls endure for millennia where our own constructions crumble in mere generations. You can see this legacy in the coastal ruins at Caesarea Maritima, where breakwaters submerged in the aggressive Mediterranean saltwater still stand, their surfaces pitted but their structural integrity unbroken. This durability was not limited to the coast. From the humid heat of North Africa to the freezing winters of northern Britain, Roman concrete proved its resilience, enabling ambitious projects like the massive baths of Caracalla and the sprawling aqueduct networks. So why did such a transformative recipe vanish for over 1,000 years? The knowledge was not lost in a single moment, but faded as the complex trade networks that supplied the specialized pozzolana collapsed, and the institutional expertise required for its precise mixing and curing dissipated. The Roman Empire did not just fall politically, its very building blocks were forgotten. This mastery over material, turning volatile earth into eternal stone, makes you wonder what other foundational technologies we have yet to rediscover. Such precise construction demanded an equally precise way of seeing the world, a need that gave rise to the instruments that first mapped these monumental forms. Precision in construction begins with precision in sight. Before a single stone of an aqueduct was laid or the path of a Roman road was cleared, ancient engineers faced a fundamental challenge: how to impose perfect lines and angles onto the unpredictable landscape. Their solution was a suite of elegant instruments, the Greek dioptra and the Roman groma, devices that turned human vision into a tool of measurement. The dioptra was essentially a precision sighting tube mounted on a flat, circular plate. An engineer could peer through it, aligning the crosshairs on a distant staff held by an assistant, and by rotating the plate against a calibrated scale, he could measure horizontal angles with remarkable accuracy. The Romans favored the groma, a simpler but equally effective tool. Picture a tall staff with a horizontal crossarm from which plumb bobs hung on strings. By sighting along the lines created by these weighted strings, a surveyor could establish perfect right angles and straight lines across vast distances. Modern land surveyors who have studied replicas express deep respect for these tools, noting that while they required immense skill and patience to use, their fundamental principles of alignment and angle measurement are identical to those in the electronic theodolites used today. The military applications were immediate and vital. A Roman legion on the march could use a groma to lay out a perfectly square, fortified camp each night, a task completed with practiced speed that provided security and order in hostile territory. For civil engineering, these tools were indispensable. The legendary straightness of Roman roads, some stretching for hundreds of miles with only gentle, calculated curves, is a direct result of the groma's unwavering lines. The gentle, consistent gradient of an aqueduct channel, which could not deviate more than a few inches per mile, was verified and maintained using the dioptra's precise angle readings. Imagine a team of surveyors on a hillside, one peering through the dioptra while another moves a marker rod far in the distance, their shouted commands carrying on the wind as they slowly, painstakingly map the path of a future waterway. The intellectual leap here is profound. It reveals a society that had mastered the abstract mathematics of geometry and could then translate those pure ideas into physical reality on a colossal scale. What kind of mind first conceived of using hanging weights and a narrow line of sight to conquer the chaos of the terrain? This was not just about building things, it was about imposing a human idea of order upon the world itself. The legacy of these tools is written across the ancient landscape, in the arrow-straight roads and the enduring alignments of city grids, a silent testament to the power of measured sight. That same drive to find direction in a vast and featureless world would soon be applied to the greatest wilderness of all, the open sea. A guiding fire in the darkness could mean the difference between a safe homecoming and a shattered hull upon the rocks. The most legendary of these beacons was the Great Pharos of Alexandria, a tower of such immense scale and ingenuity that it earned its place among the 7 wonders of the ancient world. Built during the reign of Ptolemy II in the 3rd century before the Common Era, this structure was said to soar to a height of over 400 feet, a staggering feat of engineering for its time. Its purpose was as practical as it was monumental: to safely guide ships into the bustling harbor of the greatest port city in the Mediterranean. Ancient writers like the Roman traveler Strabo described a multi-leveled marvel with a broad square base, an octagonal midsection, and a cylindrical top where the fire itself burned. But the true genius of the Pharos was not just its height but its optical system. Historians believe its architects employed massive, polished bronze mirrors, curved and positioned to act as a powerful reflector. This was not a simple bonfire. It was a focused beam, amplifying the light from a great furnace and projecting it far out to sea, a lighthouse in the truest sense of the word. Imagine the awe of a sailor after weeks on the open water, finally spotting that distant, concentrated gleam cutting through the night, a star born from human hands. The engineering challenges were immense. Building a structure of that magnitude on the shifting sands of a small island required a deep understanding of foundations. Legends suggest the architects laid its base upon massive blocks of glass to resist erosion, a testament to their innovative problem-solving. Maintaining the beacon was a constant, dedicated effort, requiring a steady supply of fuel hauled up the tower's spiraling ramp and a team of keepers to tend the fire and polish the great mirrors. The economic impact was profound. By making the harbor accessible day and night, the pharaohs secured Alexandria's status as the central hub of Mediterranean trade, attracting merchants, goods, and ideas from across the known world. This was a machine that powered an economy with nothing but fire, stone, and reflected light. How did this mastery of optics and maritime safety influence later technologies? The principles demonstrated at Alexandria of using reflective surfaces to control and project light would echo through the centuries, eventually finding their way into the telescopes and projectors of the modern age. This brilliant, ancient guidance system, a sentinel of fire and bronze, illuminates a civilization's drive to conquer not just the sea, but the very darkness itself. That same desire to impose order on a fundamental natural force would soon be directed inward, to the relentless and precise measurement of time. Long before the mechanical tick of a clock, the most reliable measure of time was the steady drip of water. From the courts of Egypt to the philosophical schools of Greece and the imperial observatories of China, civilizations independently crafted clepsydry, or water clocks, to give structure to the day and night. These were not mere buckets with a hole. The simplest form was an outflow clock, a ceramic vessel filled with water that would drain through a small aperture at a constant rate, with markings on the inside wall indicating the passing hours as the water level fell. The real innovation, however, came with the inflow clock. This design used a constant water source to fill a receiving vessel, where a float would rise, often connected to a gear train that moved a pointer across a dial. This transformed a simple flow into a mechanical display, a direct ancestor to the clockwork that would follow centuries later. Horologists who study these ancient timepieces note their surprising accuracy, though they were not without limitations. The rate of water flow could be affected by temperature and water pressure, and sediment could slowly clog the outlet. The genius of their design lay in the calibration. The scale of hours on the dial was often adjustable, with different markings for the long days of summer and the short days of winter, reflecting a sophisticated understanding of the sun's changing path. One of the most magnificent public examples was the Tower of the Winds in Athens. This octagonal marble structure, built in the 1st century before the Common Era, housed a massive water clock inside, likely fed by a stream from the Acropolis above. Its public dial would have allowed every citizen to coordinate their activities, from business in the agora to appearances in the law courts. In these legal settings, water clocks were essential, with speeches and arguments strictly timed by the flow from a designated vessel, ensuring a fair and equal hearing for all. This regulation of daily life extended to sacred rituals, where the precise timing of ceremonies was believed to maintain cosmic order. What does it say about a society when it chooses to parcel out its most precious resource, time itself, using the flow of another, water? This mastery over the intangible hours paved the way for a different kind of control, one directed at the very soil that fed these great civilizations. The silent revolution of a civilization begins not with a weapon, but with a seed. While empires rose and fell on the strength of their armies, their true foundation was the ability to feed the millions who built their cities. In the Fertile Crescent of ancient Mesopotamia, evidence points to an agricultural breakthrough that would not become common in Europe for thousands of years: the seed drill. Cuneiform tablets and certain artifact fragments hint at a device that could have been a primitive planter, a tool that deposited seeds into the soil at a consistent depth and spacing, rather than simply scattering them by hand. This was a profound leap in efficiency. A farmer using a seed drill would waste far less precious seed to birds or the wind, and each sprout would have the space and nutrients it needed to thrive, dramatically boosting the yield from every field. Agricultural historians are deeply divided on the interpretation of the evidence. Some argue that the descriptions are too vague and that the artifacts could be parts of other tools entirely. Others, however, see a clear line of reasoning, suggesting that Mesopotamian farmers had grasped the mechanical principles of leverage and material flow necessary to create a simple, wheeled device with a tube that guided seeds from a hopper into a furrow. Imagine the difference this would have made. Instead of a field of uneven, crowded shoots, you would have perfectly aligned rows of grain, each plant given its best chance at life. The benefits are undeniable, a concept proven by later, well-documented versions like the multi-tube seed drill invented in China during the Han Dynasty, and the famous mechanical horse-drawn drill popularized in 18th century Europe. To see the principle in action today, just look at a modern farm where massive tractors pull intricate planters that perform this exact same function with digital precision, a direct technological descendant of that ancient idea. The core advantage remains unchanged, maximizing the food produced from every inch of land. So why did such a brilliantly practical invention not sweep across the ancient world? The knowledge may have been a closely guarded secret of a particular region, or perhaps the specific social structure with its abundant manual labor did not create the pressure needed for its widespread adoption. It is a haunting thought that a technology capable of preventing hunger could simply fade from memory because the right conditions to sustain it were not there. This glimpse into ancient farming reveals that the most vital machines are often the quietest, the ones that work the earth to sustain life itself. And just as civilizations learned to orchestrate the growth of crops, they also discovered how to orchestrate sound, building machines that captured the very rhythm of the human heart. The roar of the Roman crowd was not just for gladiators, but for the thunderous music that filled the amphitheater. This powerful sound often came from the hydraulis, the ancient world's first pipe organ, and a masterpiece of engineering. Its inventor was Ctesibius of Alexandria, a brilliant mind who saw the potential in harnessing water and air. His device used hand pumps to force air into a chamber partially filled with water, creating stable pressure. This pressurized air was then released through a set of pipes by pressing keys on a primitive keyboard, producing notes that could be both delicately melodic and shockingly powerful. Musicologists who have studied ancient accounts describe its range as vast, capable of everything from hauntingly soft tones to a blaring fanfare that could rise above the din of tens of thousands of spectators. The water was the key to its consistency, acting as a natural regulator that smoothed out the pulses from the pumps and provided a steady stream of air to the pipes, a revolutionary solution for its time. This instrument became a staple of public spectacles, its majestic sounds underscoring the drama of the games and adding solemnity to religious ceremonies. It was a symbol of status and technological prowess, a blend of art and science that fascinated all who heard it. Modern reconstructions, built from ancient descriptions, allow us to finally hear the voice of this machine. The sound is uniquely rich and organic, a deep, breathy resonance that feels both ancient and immediate. Hearing it today makes you wonder about the role of complex technology in ancient entertainment. Was this intricate device, with its pumps and valves and water tank, created solely to elevate human emotion through music? The Hydraulis demonstrates that engineering and artistry were never truly separate in the ancient world. This same brilliant understanding of pressure and force used to create harmony would soon be directed toward a much more destructive purpose on the battlefield. The sea itself seemed to burn. In the heat of a naval battle, Byzantine dromon warships unleashed a terror that defied all contemporary understanding of warfare, a liquid fire that water could not extinguish and that clung to enemy ships and sailors with a supernatural tenacity. This was Greek fire, the most feared and secret weapon of the ancient world. Historical accounts from besieged armies describe a nightmarish scene, with streams of flame roaring from bronze tubes mounted on the prows of Byzantine vessels, the very ocean set ablaze around them. The composition of this incendiary mixture was the state's most closely guarded secret, a formula known only to a select few, perhaps even the emperor and a single family of chemists. Modern analysis suggests it was likely a volatile cocktail of crude petroleum, pine resin for thickening and adhesion, and other chemicals like quicklime that could ignite upon contact with water. This was not merely a weapon, but an early and devastating form of chemical warfare technology. The machines that projected it, the siphons, were engineering marvels in their own right. They were not simple flamethrowers. Historians believe they consisted of a pressurized pump, a heated bronze tank to keep the mixture volatile, and a nozzle where an ignition source, likely a torch, would set the stream ablaze as it was ejected. A crew of operators would work the pump, sending a continuous jet of fire across the water, a terrifying spectacle that could turn the tide of an entire battle in moments. The psychological impact was as potent as the physical destruction. Imagine the sheer horror of an opposing sailor, for whom fire at sea was the ultimate dread, watching a liquid flame that defied their every effort to douse it, a weapon that seemed to possess a malevolent will of its own. During the great sieges of Constantinople, these projectors mounted on the city walls rained fire down upon attacking fleets, creating an impassable wall of flame that secured the empire's survival for centuries. This awesome power forces a difficult reflection, a question that echoes through the ages from the moment of its invention. Where is the line between a tool for a civilization's preservation and a weapon of terrifying, indiscriminate brutality? The mastery of chemistry and pressure that created Greek fire represents a profound technological achievement, yet its legacy is shadowed by the immense suffering it caused. This ancient arms race, focused on harnessing the elements for destruction, stands in stark contrast to another form of ancient machinery, one dedicated to the peaceful, intricate art of creation. The softest threads held the fabric of civilization together. Long before the hum of modern factories, the rhythmic whisper of the spinning wheel and the steady thump of the loom were the sounds of industry in the ancient world. In societies from the Indus Valley to the Nile Delta, the creation of textiles evolved from a painstaking handcraft into a mechanized process, a quiet revolution that clothed empires and fueled global trade. The journey began with a simple drop spindle, a weighted whorl that spun fibers into thread by hand. But the great leap forward came with the invention of the spinning wheel, a device that used a drive band and a large wheel to rapidly rotate a single spindle, allowing a spinner to produce thread with unprecedented speed and consistency. This was automation on a human scale, transforming fluffy cotton or flax into a strong, even yarn ready for the loom. Textile historians point to India as a probable birthplace for this technology, where evidence of cotton spinning wheels dates back millennia. The principle was brilliantly simple, yet it multiplied a worker's output dramatically. turning thread from a precious commodity into a foundation for vast economic networks. The loom was the spinning wheel's powerful partner. Early horizontal looms, where threads were stretched across a frame, gave way to more complex designs like the vertical two-beam loom used in ancient Egypt. But the true marvel of mechanical ingenuity was the treadle loom. This machine incorporated foot pedals connected to a series of lambs and heddles, devices that raised and lowered specific warp threads, the longitudinal fibers that form the backbone of the cloth. With a weaver's hands now free to throw the shuttle carrying the weft thread back and forth, the process became faster and far more versatile. Imagine the coordination, the dancer-like rhythm of feet pressing pedals while hands guide the shuttle, all to create intricate patterned fabrics that were once impossible. Archaeological finds provide stunning evidence of this mastery. From the linen wrappings of Egyptian mummies, woven with threads so fine they rival modern textiles, to vividly colored woolen fragments from Peru featuring complex geometric patterns, these artifacts are a testament to the loom's capabilities. Each preserved textile is a frozen moment, a record of a weaver's skill amplified by their machine. How did these devices support entire economies? The production of cloth became a primary engine of trade. Luxurious Chinese silks, delicate Indian cottons, and sturdy Roman woolens were transported along the Silk Road, becoming currencies of status and diplomacy. The efficiency of these spinning and weaving machines meant that a single household could produce surplus cloth, a valuable good that could be traded for food, tools, or other necessities. This mechanization of a daily task did more than just cover bodies. It built commercial networks that connected continents. The intricate interplay of gears, pedals, and shuttles in these ancient workshops represents a different kind of celestial clockwork, one that mapped patterns not in the stars but in the very threads of human life. This earthly mastery of rhythm and cycle logically turns our gaze upward, to the great stone machines that sought to decode the grandest patterns of all. The architecture of the Maya was a machine carved from stone, engineered to watch the sky. At sites like Chichen Itza, the observatory known as El Caracol stands as a silent testament to this celestial obsession. Its unique circular tower, rising from a broad platform, is pierced with narrow windows and doors that are not randomly placed. Archaeoastronomers who have studied these alignments confirm their stunning precision. The main sightline from the central window frames the path of Venus, the brilliant evening and morning star that held profound significance for Maya cosmology. Other openings align with the solstice sunsets and the northernmost setting of the moon. This was not a temple for occasional ceremony, but a dedicated scientific instrument, a permanent observatory designed to track the complex cycles of the heavens over generations. The Maya did not just observe, they calculated. Their astronomical records, kept in intricate codices, reveal a civilization that could predict planetary movements and eclipses with an accuracy that would not be matched in Europe for centuries. They understood the 584-day cycle of Venus and the lunar month to within a few hours. This required a staggering level of mathematical sophistication, including the development of the concept of zero and a place value numbering system that allowed for calculations into the distant past and future. How did they achieve such precision without optical lenses? They likely used simple but effective tools like sighting tubes made from hollow bones or reeds to isolate a single star or planet against the dark sky, minimizing atmospheric distortion. The most vivid example of this cosmic alignment happens every equinox at the Pyramid of Kukulkan. As the sun sets, the play of light and shadow creates the illusion of a serpent slithering down the northern staircase, a fusion of architecture, astronomy, and mythology that united the community in a shared, predictable spectacle. This deep, codified knowledge of the cosmos was inseparable from their daily life, governing agriculture, ritual, and the very structure of their elaborate calendar systems. Why would a civilization invest so much of its intellectual capital in mapping the sky? For the Maya, the celestial realm was not a distant abstraction. It was a living, breathing influence on the world below, and by understanding its rhythms, they believed they could maintain the balance of existence itself. Their stone observatories were machines for navigating time, a grand and enduring attempt to find human meaning in the vast, orderly clockwork of the universe. This profound cosmic connection brings our journey to its final, and perhaps most personal, mechanical wonder. The final machine in our journey measured the very ground empires walked upon. For the sprawling Roman road network to function, distance had to be more than an estimate. It had to be a known, standardized fact. The Roman architect and engineer Vitruvius described a brilliant solution, a device mounted on a carriage that audibly clicked off each mile, the odometer. Its mechanism was a masterpiece of practical gearing. As the carriage wheel turned, it engaged a series of interlocking cogwheels. Through a precise train of these gears, the rotation of the large wheel was translated step by step, until after exactly 1 Roman mile, roughly 4,860 feet, the final cog in the sequence completed a single revolution. This final rotation would then tilt a small lever, causing a pebble to drop from a hopper into a metal box with a distinctive clink. At the end of a day's journey, the driver or a military surveyor would simply count the stones to know the exact distance traveled. Historians of technology who have reconstructed this device highlight the mathematical elegance of its gear ratios. They calculate that for a standard Roman carriage wheel with a diameter of about 4 feet, it would take 400 revolutions to cover 1 mile. The gear train was therefore designed with a 400-to-1 ratio, a complex but achievable feat of bronze gear cutting that transformed a continuous journey into a series of countable, tangible objects. Mentions in other texts, like those of Heron of Alexandria, confirm this was not just a theoretical idea but a tool in use, crucial for the precise planning that built the straight, enduring roads which still crisscross Europe today. Imagine the sound of that stone falling into the box, a quiet, mechanical confirmation of progress across a vast landscape. This was engineering in service of logistics and control, enabling the Roman military to calculate march times and supply lines with an accuracy that bewildered their adversaries. How did such a practical invention influence the world that came after? The principle of the odometer, of translating motion into measurement, is the very foundation of all modern navigation, from the trip meter in your car to the pedometer on your wrist. Reflecting on these 25 machines, from the cosmic computer of Antikythera to the mile-counting carriage of Rome, we are left with a profound question. What does this forgotten age of scientific mastery reveal about our own civilization? Each of these devices represents a spark of genius, a solution to a fundamental challenge, yet so many of these flames were extinguished by time. They whisper that human progress is not a straight, inevitable line upward, but a story of brilliant peaks and deep valleys. The legacy of these ancient machines is not just in their mechanics, but in the enduring human spirit of inquiry they represent. A spirit that reminds us that our greatest achievements are only permanent if we choose to remember them. That steady click of a Roman odometer counting miles echoes a haunting question. Why did so many of these brilliant machines simply vanish from human memory? The perfection of a Roman aqueduct, the calculations of an Antikythera gear train, the chemical mastery of Greek fire, these were not isolated accidents. They point to a world where scientific understanding had reached peaks that would not be seen again for over 1,000 years. Historians who study these patterns point to a recurring theme in human history: the fragility of knowledge itself. Our story is not one of constant upward progress, but of steep ascents followed by devastating descents into what scholars term technological regression. The most dramatic example is the Late Bronze Age collapse, a period around 1200 years before the Common Era, when a single, interconnected world of empires and trade from Greece to Egypt disintegrated within a generation. The causes are still debated: a combination of climate shifts, mass migrations, and internal rebellions that shattered the complex economic systems supporting these civilizations. With that collapse, the skills of literacy, monumental architecture, and international commerce faded across the Mediterranean. The intricate art of carving linear B script on clay tablets was utterly forgotten in Greece, not to be replaced by writing for centuries. This was not a slow forgetting, it was a civilizational blackout. Another profound loss was the destruction of great libraries, those repositories of accumulated wisdom. The legendary Library of Alexandria stands as the most famous symbol of this tragedy. While its final destruction was a slow process of fires and neglect over centuries, the loss was incalculable. It was not merely a building that burned, but a universe of data, the written records of experiments, star charts, and mechanical designs from generations of thinkers. One historian of science notes that when a library dies, it is not just books that are lost, but the very questions that previous ages knew how to ask. Without those written foundations, each new generation must start from a much lower base, rediscovering principles that were once well understood. How does knowledge survive such a catastrophe? Often it does not. What remains is frequently preserved in fragmented, fragile forms. An oral tradition might keep the legend of a great flood, but it cannot transmit the precise engineering specifications for a water screw. A single surviving manuscript, copied and recopied by monks with no understanding of its contents, might preserve a mathematical theorem, but the context for its use is gone. This is why we find hints and whispers instead of complete blueprints. The gears of the Antikythera Mechanism are a perfect example, a device so advanced it stands completely alone in the archaeological record, with no clear technological ancestors or descendants. Its existence implies a school of thought, a community of engineers whose other works are simply lost. Look at a timeline of human innovation, and you will see these peaks and troughs clearly. A golden age of invention in Hellenistic Alexandria is followed by a long, slow decline. The Roman mastery of concrete and hydraulics gives way to centuries where such large-scale projects were impossible. The brilliant astronomical predictions of the Maya fade into silence. This cyclical pattern forces a sobering reflection for our own time. What foundational knowledge do we take for granted that could be lost in a single generation of disruption? Our digital records, our global supply chains, our specialized sciences, are they any more permanent than the scrolls of Alexandria? The story of these 25 ancient machines is not just a catalogue of wonders. It is a profound lesson in the stewardship of knowledge, a reminder that every advancement carries with it the quiet responsibility to ensure it is not forgotten. Our journey through these 25 ancient machines forces a complete rethinking of history itself. We are not simply looking at clever inventions, but at a forgotten age of scientific mastery that rivals our own in its ambition and sophistication. From the celestial gearwork of the Antikythera Mechanism to the self-healing Roman concrete that still stands, these were not isolated accidents. They represent a diverse tapestry of innovation woven across continents, from the precision stonework of the Inca to the chemical genius of Chinese alchemists and the mechanical theaters of Hellenistic Alexandria. This was a world buzzing with intellect where the fundamental principles of physics, from steam power to electricity, were not just understood but actively applied. The most haunting lesson, however, is not their creation but their disappearance. Time and again, we see that the flame of knowledge is fragile, easily extinguished by social collapse, the loss of a library, or simply a shift in economic necessity. This cyclical pattern of peak and decline challenges the comforting idea of linear progress, revealing that our own technological civilization is not a guaranteed endpoint, but another chapter in a long and unpredictable story. It calls for a profound humility, a quality beautifully captured by the astronomer Carl Sagan, who once reflected that you have to know the past to understand the present. Our ancestors were not primitive, they were pioneers whose legacy whispers to us from the silent gears of a recovered clock and the perfect seams of a granite wall. Their achievements ask us to reconsider the full scope of human potential. What other forgotten wisdom lies buried, waiting to change our story once more? If this exploration has reshaped your view of history, we encourage you to continue the journey. Visit a museum with a new perspective, or pick up a book on these incredible technologies. And we would love to hear from you. Which of these ancient machines captured your imagination the most? Was it the roaring power of Greek fire, or the silent, patient intelligence of the Qanat? Share your favorite in the comments below and join our community of curious minds. For more journeys into the world's greatest enigmas, be sure to subscribe. The past is not as distant as it